In this last video on greedy algorithms, we are going to discuss Huffman trees, which are a special type of trees that are actively used for compression of text. Like what I mean by compression is, like let's say if you have a very large file and you want to send that file over the internet, you might want to reduce the size of the file without altering the meaning or the essence of the data in the file, which is like, let's say if I wanted to send a file that contains 10 characters like apple is good, I cannot do something like I just delete apple, like I just send apple is, I delete the good part and just send the file to reduce the size. What I might want to do is I want to identify patterns in this data. Like let's say if it is something like this, which is A, and then B, and so on. I might want to identify patterns in this data to compress the file. You might have already seen an example of this, like those of you who took programming 1, which is the COP 3502 course. If you remember, you did the run length encoding in project 2 of that course, where you essentially compress this in the form like A4, B3, and C2. Like that is one way to change this data, which is you have this data, this is the raw data, and you converted it into encoded form. Like that is one algorithm to encode that data. So today we are going to see actually Huffman trees. We'll first learn what are the principles. These trees are important because they are used, like currently also they are used because they neatly compress the data and reduce the amount of like data that you want to transmit over the internet. So let's get started with Huffman trees. It's a special case of like greedy algorithms, like the algorithm that is used for compression, which is encoding and decoding in these trees, is essentially a part of greedy algorithms, and how you construct it is also like a greedy algorithm. So how it works is like the first thing I wanted to discuss was how do you think like text is transmitted, which is like, let's say if you have like a large file or anything that you want to transmit over the internet, or you want to move from one person's laptop to another, all of this is essentially encoded in the form of zeros and ones, because computers only understand zeros and ones. So we have kind of a system that abstracts every character that we have into zeros and ones, which is like, let's say if you want to represent A, what we might want to do is A is internally coded as 65 based on ASCII value, and this ASCII, whenever we want to transmit A over the internet, what we might have is, we have decided like since A is 65, we are going to represent the number 65 in 8 bits or 16 bits, depending on the protocols that we have designed for transmitting text over the internet. Like let's say if it is 8 bits, what we might do is we will convert this number. I'm just using like a fake number, but let's say if 65 converts to whatever, like the number doesn't matter, but the key idea here is that we change the 65 into like 8-bit codes and transmit over the internet, or whenever we have any type of data, we change that into binary. So that is one of the important things to note. Another thing is, like whenever we have a character set, which is like, let's say if we have A and B, like two values, and we want to represent these characters using unique bits, how many bits do we require to represent, like let's say if we have 2 characters. So to represent 2 characters, you would require like 2 bits, because 1 bit, because 1 bit can actually identify 2 unique characters, which is you can have 1 bit actually represent 0 and 1. So essentially you can code A as 0 and B as 1, or B as 0 and A as 1, or vice versa. Okay. Now if I have 2 bits, like let's say if I have 2 bits, how many unique information can I code, which is in this case it will be 2 to the power 2. Okay. If there are 3 bits, it will be 2 to the power 3, and so on. Like this is like the general pattern, because if you have 2 bits, you have like 4 unique values, which is 0, 0, 1, 0, 1, 1, and 0, 1. and you can store, like let's say if you have A, B, C, D, you need at least like 2 bits to represent 4 different characters. So like let's say if we have 128 characters in the ASCII table, how many bits do we require? So this is like a general formula that we are trying to derive, which is when we had 3 bits, we required 2 to the power 3 different, like we could represent 2 to the power 3 new information. So now I'm asking the other way, which is 128, like if you represent this in the form of 2 to the power, so 2 raised to the power 7 is actually 128. So essentially you would require like 7 bits, which is just by symmetry, okay? Which is the key idea here is that like you would require log n base 2 number of bits to represent like a character set that consists of n different characters. So let's say if we had, again, like if we had 4 characters that we want to represent, like let's say if we have A, B, C, D in our character set, we can just take the log base 2 of 4 and take the seal of that value to get the number of unique bits that we would require. Like this is important because this is going to show you how we contrast like what sort of compression is actually being generated. So in this case it would be like this can be represented as 2 to the power 2, which can be 2 log base 2 and then 2, and this is actually 1. If you take the seal of this number, that's 2. So essentially you have ABCD requires like 2 bits, which is like if you have 0 0 0 1 1 0 and 1 1, that can actually represent like this character set. So let's try to discuss how many number of bits would we require. Like let's say if you want to transmit this string and this is the only characters that we have, like consider a hypothetical world. So I have this word called Mississippi. What I'm going to do first in this word is I'm going to see how many different characters it has. So it has M, I, S and P. Those are the 4 characters. So again, since we have 4 characters, we require like log base 2, 4 and seal of this number, which is essentially like 2 bits. Okay, so one character actually requires 2 bits for its representation at minimum, and this string itself has 11 characters. So the total amount of data that would be required to transmit Mississippi is going to be 2 times 11, because each character requires 2 bits and we require like 11 bits. Now let's say if we had a file that just had this Mississippi, we were transmitting over the internet, we require 22 bits of data. Like this is the threshold that we are dealing with. You'll see like when we generate Huffman tree, this is kind of the baseline that we are working with. We want to reduce this number because Mississippi is a hypothetical example. Let's say a file contains like trillions of words, okay? Like it's a dictionary or something. So in that case, how do we compress text? That's what we are trying to represent, which is the ideas are exactly the same. Because we have a character set, the character set determines how many characters we have, and based on these characters, we actually use the concept of entropy. Like if some of you have learned this in physics, we are basically using the bits entropy to represent this information, which is we are trying to communicate, which is like whatever the character set is, we are trying to represent it with unique symbols. So essentially, how does the Huffman algorithm work is, I'm going to first show you the steps because it's easier to see the steps, and then you'll see the bigger picture on how this works. Which is whenever we have a text, like let's say if it is Mississippi, in this case, the first thing we are going to do is we are going to create a table consisting of the characters in that text and the frequency of the characters, which is in this case M is only typed once in Mississippi, I occurs 4 times, S occurs 4 times, P occurs 2 times, and so on. So the big idea in this algorithm is that like when we had these 4 characters, we represented these 4 characters using like 0001, 10, and 11, which was some arbitrary coding scheme that allowed us to map these characters to send them across the internet, because the person who's sending them has these codes, and the person who's reading it on the other end also has these codes. So they receive these bits, and based on like a simple transmission scheme, they would just change, like let's say if it is 0001 and so on, what they would do is they would take 2 bits at a time and change 00 to M, because they have like a one-to-one map of what do the bits represent. Now what Huffman trees do here is they take this property that some characters here are more frequent than another, which is in this case I and S have like occurrences of 4, while M occurs only once and T occurs only 2. So the general idea of the algorithm is how can we reduce that to make codes smaller for more frequently occurring characters, which is what if we can represent like the code for I with like no value or one bit rather than 2 bit, while for M maybe we can represent 3 bits and so on. So that is the general idea. But the key step, the first step, was to generate this frequency table. The next step is to construct a set of trees with root nodes that contain each of the individual symbols and their weight. So I did nothing, but I took one row at a time, which is the character and a frequency, and I created like a tree object where each tree represents like these are individual Huffman trees, okay? And each tree represents a character associated and its associated frequency count. That's all I did. Next, what we do is we store all these different Huffman trees into a priority queue. And this priority queue uses the frequency of these characters, which is these characters, as the default priority. So you'll see that in a little bit, like how this works. Then what we do is, while the priority queue has more than one item, so we run a loop and check if the priority queue has more than one item, you remove the 2 trees with the smallest weights, which is, this has to be a min priority queue, not a max priority queue. So a min heap, essentially. We take the first 2 items. What we do is we combine these 2 to generate a new node, and that new node represents like any, like it should not have any character. You can either define it as a separate new node or you can have like an arbitrary character that is not a part of the character set that denotes the character, but the values would be the sum of these 2 nodes, which is in this case it's going to be 3. Okay, so combine them into a binary tree. So essentially the tree is going to be always binary. The Huffman trees are going to be binary, in which the weight of the tree root is the sum of the weight of its children. That's the key idea. Next, we insert this tree back again into the priority queue, which is the next step, which is you first join these 2 to get this value 3, and then you insert this back into the priority queue. That's all I did. And you repeat this again and again till the tree is generated. Now what will happen next is the queue is not empty. So we take out the 2 values from the queue, which is in this case these 2. It could be S or I, it doesn't matter. You could have multiple Huffman trees representing the same file, because like you can pick, depending on your implementation, you can pick any of these weights because they have equal weight. So essentially you join these 2 again and create a new node with the value that is the sum of these 2 nodes, which is in this case 7. Next, you again push this tree back into the priority queue, and now you combine these 2, because these 2 are the last 2 elements, to again join and create the sum, which is 11. So essentially this number 11 in a Huffman tree will represent the total number of characters in the file that you're trying to send. So whenever you have a file or a text, you would not have a pre-computed Huffman tree. What you would usually have is you create the Huffman tree of that particular data based on the patterns in the data, which is the first thing the algorithm would do is it would generate the Huffman tree. It would not use a pre-computed Huffman tree, like unless we have the same files which we can detect using by taking the hash of that file. We discussed hashing a while ago. If you don't know that, look into those videos. So then we push that back, and since it has only one item left, we just end the algorithm right there. So now the key idea is, how do we generate the codes from this Huffman tree? So this is the Huffman tree. The idea behind generating codes is, if you go towards left, like you start from the root node, whenever you go left, you add a 0. Whenever you go right, you add a 1. So different books follow different conventions. Some books follow the opposite one, which is you go towards left, you do 1. You go towards right, you do 0. But we are going to stick to, you go towards left, 0, and 1 is going to be towards right. So let's say if I want the code of a particular node or a particular character, in this case I, what I'm going to do is I'm going to start the traversal from the root node and go to all its leaves, because these are the leaves, and each leaf represents a character. So essentially the code for I, as you can see here, this code is 0 because you just traversed one left. When we talk about M, this will be 1 and then 0 and then 0. So essentially M, you can see it's 1 0 0. Then when we talk about P, it's 1, then 0 and then 1, which is this code. Then finally the last one is S, which is 1 and 1. So you can see S is 1 1. Now here, if you calculate the frequencies of these characters, which is we already have those in the table, you see the number of bits for the code that has been generated. This is called Huffman code. The number of bits in this code is 3 for this one, 1 for this one, and 2 for this one, and 3 for this one. If you multiply this bits per code by this frequency, what you essentially get is the total number of bits that are required to transmit Mississippi using the Huffman tree or the Huffman codes which you have just generated. This process is called encoding, which is you translated Mississippi into the binary form using these values, which is, it should be 1 0 0, then I is 0, then S is 11, then S is 11, and so on. So you'll have a long string like this. And since the tree is designed in such a way that how you can decode this is let's say if you get these values, you start from the root node, and what you do is you if you have a 1 here, you go towards the right, and if you have a 0 here, you go towards the left, which is the same idea, which is you are reproducing the code in the same way you generated it, which is you start here. So we have 1 0 0 0, so 1 would take us here, 0 would take us here, and 0 would take us here. Whenever we reach a leaf node, you just replace the traversal of the codes, which is 1 0 0, will be replaced by M. So the receiver is also going to have access to this Huffman tree, which is they have this code. When they pass this string of zeros into the Huffman trees, you can again decode it back to get Mississippi back. So essentially you saw M is being generated. Then you have 0. So 0 will take us to the leaf node. So you can replace this 0 with I. Then you have 1 1, which is 1 1 is going to take us to S. So this 1 1 is going to be replaced with S. So this is how you decode characters. Now, if we calculated the total amount of bits that are required using this method, it's roughly 21 bits, which is, earlier we required 22 bits when we started, because each of them were being represented by 2 characters, 2 bits each, which included 2 into 11, which is 22, but now it's 21. So this is a compression of the compression ratio is now going to be 95.5%, which is essentially we just saved about 5% of the transmission. Like 5% is a very small number, but this was a very trivial example. Like let's say if I just make one change here, which is instead of Mississippi, if I use a text where Mississippi's has I's that are followed 1,000,000 times, what you see here is that the tree and the codes will remain the same, because I also had the highest frequency earlier. Now also it has the highest frequency, so it will be up in the tree. The codes look exactly the same, which is like you can see the Huffman tree for this one would be exactly the same. Now if we calculate the total bits for the Mississippi, you would see that we would require roughly 1,021 bits to transmit Mississippi. But if we use the regular transmission method, which is the 2-bit for every character, what we require is roughly about 2 million bits. So essentially our compression ratio is roughly 50%, which is now we are saving a lot of bandwidth or lot of like processing power that we might be required to like send this data. Okay, so essentially that's the gist of it, which is we are now reducing a lot more space. So this compression ratio can never exceed 1 because of the mathematical properties of how this algorithm work. But that's the gist of it. Here is kind of like a simple class on how to represent Huffman tree. You don't have to do this, but this was an earlier project, so I'm using the slides for this. So we are not doing the Huffman tree project this time. So, but this is the general idea of the Huffman tree, which is you like if you're generating the Huffman tree algorithm, you might have different functions that would represent the Huffman tree. The get character code. This is how you like modularize your code. You might have an encode and decode function, which encodes a particular string into like ones and zeros, and decode takes in a long string that is represented as binary, and it returns a plain text in string format. So that's the gist of it. This is the key idea, and it's like frequently used. So I hope you understood it. If not, like feel free to ask me any questions during my office hours. Thank you.